Okay, so here we are in the new CGP Pure book, page 281, example 2. We're told about the position vector of 2 points, and we're asked to find the length of AB. So that symbol there, which we're used to seeing meaning modulus, in this case means the length of that vector. And I do not like the way they do it, so I'm going to show you how I would do it. Okay, so surprise, surprise, I've drawn the vectors in column form, and I'm going to draw a little picture. So there's the origin, there's point A, there's point B. No attempt to make them look vaguely realistic. That's 3, 2, 4, that journey, and that's 2, 6, minus 5. So the vector AB, that is backwards down there and up there, minus 3 plus 2, minus 2 plus 6, and minus 4 minus 5. And so, as I said in the last video, finding the length of AB is just three-dimensional Pythagoras. Again, it is the square root, and it's minus 1 squared plus 4 squared plus minus 9 squared. So that's the square root of 1 plus 16 plus 81. Sorry, gone off the page there. And so that's rather funky on the visualizer. So the square root of 1 plus 16 plus 81. And there is my answer in surd form. So here we are over the page on page 282, example 3, same thing, but this time we're given the length and we've got some missing values, and also rather than giving us vectors they've given us 3D coordinates. I don't like the way they do it, so here goes my way. So I've taken the two 3D coordinates and turned them into position vectors, and I've worked out the vector AB. It's minus that plus that, that's 3 plus 2, minus that plus that gives us 7, minus that plus that gives me that, and I know therefore that the length of AB is equal to the square root of that squared plus that squared plus that squared. So got to grid that out. Here's one I prepared earlier. Oh, and I know the length is 3 root 11. We're told that in the question. So I gridded all that out. And so 3 plus 2t squared is 9 plus 12t plus 4t squared. 7 squared is 49. Minus 4 minus t gives me 16, plus 8t plus t squared, and that's 3 root 11. So I did a bit of simplifying here. So I get 5t squared plus 20t plus 74. And at the same time I said, right, 3 is the square root of 9. So 3 root 11 is the same as root 99. I've sort of unsimplified it, because what I can now do is square both sides of that equation. Square rooting, we have to think about the plus or minus thing, but when we square both sides, no such consideration. So we end up with that equation there. And take away 99 from both sides. And we get that. You'll see this is my second attempt. My 25 was originally a 27, and it didn't quite work as well. And of course we can use our calculator at this point, but you know, I'm always saying if you have time in the exam, show how you can do it manually as well. Nothing wrong with using the calculator, but this one works out quite easily. So I divide everything by 5, and then it factorises quite easily. So I'm not particularly slick at my sliding the camera down thing. And there we go. So t is minus 5. And t is minus 1. no, sorry, t is 5. Glad to see I do this even at home. T is minus 5 and t is 1. Okay, so on page 282 we're on example 4 now. Flight path of two different aeroplanes taking off from a runway, so that runway could be considered to be your origin, and they give you those two vectors, the vector of one aeroplane and the vector of the other, and we're asked to find the angle between the two flight paths. So I'm going to do it my way, although actually their way is pretty much the same here. So although there's no mention of points A and B, I'm sort of modelling it as this. So the vector A is going in this direction, so I'm treating that as a position vector going from the runway to some point A, and similarly the vector B. And what I can do then is work out the vector AB, as always. So that is backwards down there and then forwards along there, so it's minus 5 and minus 3, and it's backwards along there and up there, so that's 2 plus 3, and minus 1 plus 1 is that one. And what I've got here is a triangle, not a right angle triangle, so I can't use SOHCAHTOA, but it is a triangle, and the angle I'm trying to find is this angle here. And so this is a cosine rule question. Cosine rule is normally used where you know about a corner of a triangle, so when we know about the two sides and the angle between them we can work out this side. But you may remember that you have a rearranged version of it which you can use to work out an angle. And so if I call the angle that I'm after A, so let's call that A, the side opposite it is called little a, and the other two sides are called B and C. Now of course they're almost deliberately trying to confuse us here because we've already labelled this A and B, so I always say, right, when you're using the cosine rule, ignore the labels they've used and use the labels that the rule says. So the side opposite the angle we're trying to find is little a, so these two are B and C, and it doesn't matter which way around they go. So what I need to find out are the lengths of A, B and C. And I can do that because I've got a way of working out the length of a vector. So I'm going to pause at this point and encourage you to work out those three lengths, and then we can get together again when we've worked that out. Okay, so this is where we were. So hopefully you agree with me that the three lengths are root 89, root 30 and root 19. And of course the nice thing about the rearranged cosine rule is that it uses b squared, c squared and a squared in the numerator. So when I plug the values we've got in, I get that. Now you could ask, how do I know it's this and not, one of the other solutions for that angle? Well, I know it's in a triangle, so it's got to be less than 180 degrees, and that's the only solution between 0 and 180 that works, and I've rounded it to 3 significant figures. So that's how to find the angle between two vectors, and it uses the rearranged cosine rule. Okay, so here's some practice of those skills. Again, all in the new CGP Pure book, and let me know how you get on with them. We're very nearly there. We've just got a couple of little itty bitty things to finish off, and then we can move on to vectors and mechanics. So all good stuff.